All right, welcome everybody to the Young African Scientist platform. Today we are going to look at machine learning. We are looking at deep learning, and the person that is going to take us through is the person that took us through the introduction. That is Dr. Elvis Chumesi. So Dr. Elvis, if you're there, you can start setting up. Let's have your slides and let's start up. I've put the materials for the program in the WhatsApp group, so you can access all of it there. And this is going to be a wonderful time of machine learning together. Deep learning and neural networks and image recognition is something that takes you deeper into machine learning. And that is something that everyone would want to know if you're going to do any sort of machine learning. So thank you very much for coming around. The link for your registration is in the chat group. So I'll be posting it from time to time. You can start registering your attendance at the moment. If you don't have your code, your professional code, contact me by my email or on WhatsApp, and I'll look for that code for you. But for now, we are in the hands of Dr. Elvis. So Dr. Elvis, please take over, and you have 1 hour, 30 minutes. I know you, please don't go above that. And make sure we can keep it short and simple. All right, so please take over.
Okay, so thank you very much and welcome once again to all of us. I'm sure we met in the first class, we've not met again, and it's good we are meeting again. And it's going to be a nice time. And I believe that deep learning is one of the, if you remember my introductory class, I spoke about how deep learning is a subset of machine learning, and it actually goes with dealing with very big data, right? And almost all the new models that you are seeing, ChatGPT, Claude, and all that, they are all deep learning models, right? So it's a very good time for us to understand what deep learning is. And we are basically today going to look at how we can detect images, right? And it's going to be a nice time. We are going to have a good understanding. So I just want you to follow me through. I'll be talking plenty, but then if you have any questions to you, let me know. I have a lot of information I want to give you in this class. So just let's follow. And it's going to be as simplified as possible. So let's just kick off. Now, what's deep learning? So as I said, it's a subset of machine learning. And as we've already also said, machine learning too is just a subset of AI. So deep learning actually is what is making AI the AI you know. Anytime you hear about AI, go to ChatGPT, you ask any question, you can generate image, you can generate videos and all that. They need deep learning models. So deep learning models are machine learning models that are able to deal with large amount of data and all that, right? So while machine learning usually require manual feature engineering. I think in one of the class, we looked at feature engineering, where you have your input data and your output data. So from your input, you're able to tell that, oh, maybe you are predicting costs, the cost of a building, maybe the size of the building is there, the location of the building is there. So you have a structured data, right? So you know what the features are. But one thing is that most of the time in deep learning, sometimes you may not know the features, right? Especially take a model that you are having that you are going to have images as inputs. Now, if you have an image, the question is, which one is your features? Like, is it a person's nose or eye or something? So you realize that in normal machine learning, most of the time, the features are there, we can know. But deep learning automatically will learn these features from the raw data by itself, right? So deep learning uses it, and one thing is that most of the time we talk about deep learning, these are the models that actually uses something we call artificial neural networks. So for me to show you how to recognize image and all that, you first need to understand what neural networks are. Then we can just zoom into how we can detect images with deep learning models. So the term deep comes from the fact that the network has to have multiple layers, right? And I'll introduce you to that so that we can learn complex patterns. So imagine learning someone's face and getting to know the size of the person's nose, the shape of an eye and all that. You need some deep learning models to be able to do that. Normal models like random forest, decision tree, and all those models that we've learned will not be able to detect such images. So deep learning comes in to actually do that. So as I said, traditional ML, most of the time struggles when you have a lot of data. Can you imagine you have 1 million data sets? like ChatGPT, Gemini, and all those models that are trained with thousands of books and millions of documents and all. Normal machine learning models will not be able to deal with them. So we need deep learning models. So look at somebody's audio, like as I'm talking now, if you want to understand what is going through the audio and all that, normal machine learning models will not be able to do them. So we need deep learning models. So deep learning can handle millions of data points, and it will be able to automatically discover the patterns and everything by itself. So dense and deep layers in every deep learning model is able to understand complex patterns and everything within the model. So most of the time we use this deep learning in computer vision, which is the main part we are going to look at today, how computers are able to detect images, right? Speech recognition, someone is talking, you want to know natural language processing, and most of the ChatGPTs and all those models that we have using natural language processing what you are telling them. You'll be able to translate someone's English to French and all those models. They are all deep learning models. Now, what are the types of deep learning? So mainly we have something we call convolutional neural networks. And these are the networks that we are going to look at today in this class, convolutional neural network. Mostly it's designed for images and videos. So if you want to detect edges and textures and people's face and objects and everything, you need this convolutional neural network, which we are going to look at today. There's something we call recurring neural network, and it works well with sequential data, right? So first, when Google started, if you realize that, let's say if you go online, you are typing something, realize that there are some suggested words that come along with them, right? So these are recurring neural network. They're able to learn from the previous data that you gave them and be able to make predictions of what you're. So if somebody goes online and is typing apostle, then you realize that suggestions of Paul, Peter, and all those people can, because these are known things, right? So if you start typing the president of Nigeria is, you realize that suggestions will start coming with these recurring neural networks, and you'll be introduced to them when we have our last lecture. Then we have something called long short-term memory. And one difficult thing about this recurring neural network was that if I want to predict the next word that will come, I have to look at the word before you ask me, right? And the thing is that sometimes when I have to predict the next word, it doesn't depend only on the last word you told me. I have to look at all the sentences you have made and all. And because of that, recurring neural network had a short-term memory, right? So it's able to just know the word you gave it before it to be able to make the prediction. But this long short-term memory just came to resolve the issues of RNN, so that you'll be able to look at the entire long distance statement that you have given me before I make the next prediction for you. But these transformers came to change the issue of AI and machine learning and deep learning issues. Call them transformers. And it's not a transformer you know in a substation in electrical engineering, but these transformers are what is used in ChatGPT, in Claude, in DeepSeek, in everything. Almost all the AI models that are making waves are all transformer models. So the backbone of AI, like ChatGPT and all that, and it's excellent for handling large sequences of data. And you'll be introduced to transformers. Now, as I've already explained, recurring neural network is designed for sequential data. It has memory to retain previous inputs you give it. But then this issue was solved with the LSTM and the GRU to actually deal with the issue. So most of the time, recurring neural networks are being replaced with this LSTM and GRU. But then we have transformers, which is a deep learning model that possess sequence, is able to process sequences of data. Let's say you can ask ChatGPT a whole document and it'll be able to, in few seconds, tell you what is happening because it's able to pick all the data at the same time, deal with them and understand what is going on using something we call attention mechanisms. And it's able to tell you what is happening within your document and everything within a short time, right? And I'm sure we learn transformers and you get to know how transformers are. So it's dealing with the issues of RNN and all the, so we use them for translation. If you want to translate from English to French and all other summarization, chatbots and all those things. These are all based on transformer models. Transformer models, we have different types. We have the encoder-only transformers, and we use them for classification. So most of the time, if you want to do classification, you want to tell whether this is this sentiment analysis, and you need a transformer model to do that, you can use an encoder only. You'll be introduced to transformers, so you get to know this. You have the decoder only transformers, and that's ChatGPT and all those things are based on the decoder only transformers. And most of the time, if you want to do translation and all, you have to use something we call encoder decoder transformers. I'm not here to go deep into transformers. We are here for image detection, classification, and all. They have something called generative AI, as we are able to generate images and all. They are all based on models that we call large language models, LLM. So a transformer like this is a large language model. So these large language models are the one changing the world of AI right now. We have something called diffusion models, where you can use it to create new data and all. Then we have GANs, generative adversarial networks, and we are able to generate images with these. So we can go online, generate images and all. Mostly they are all based on generative adversarial networks. But almost most of the things, all that you see in AI, everything is mostly LLM models, large language models, always based on transformers. So large language models, these are mainly transformer models, and they can understand and generate and reason like human beings, right? So they are mostly used in chatbots, as I've mentioned, Claude, BERT, Llama, and all these models developed by large organizations. So this is just a general overview of what deep learning is, and most of the models that is changing the world of AI right now. So let's go straight into what we want to do today in terms of image recognition. But before we do that, as I said, everything deep learning starts with neural networks. Everything transformers we've spoken about, everything AI starts with neural networks. So deep learning, every deep learning model mostly have neural networks at the beginning, and we add some other things to the neural network to give the different types of neural networks, right? So whether convolutional neural network, recurrent neural network, transformer models, all of them are based on neural networks. So you have to understand what neural networks are. So neural networks are models inspired by how human beings think. And you see, AI, artificial intelligence, is that we want machines to start thinking like human beings. And mostly all of them are basically based on neural networks. And we are trying to let machines think like human beings. We have to look at how human beings think, right? So it's actually neural networks trying to actually model your brain. In your brain, you have something called neurons, which are there. And it's like this. You have this cell body or your neurons there, and there's a nucleus within your neurons inside your brain, right? And you have something called dendrites. They receive information. So when you look at things, when you you smell something and all those things, it goes through something we call dendrites and get to your neurons, and your neurons will produce an output through something we call an axon. And this axon has dendrite terminals too as well. So you realize that every time an information comes in, you process the information within your brain, and then you bring it out, right? But your brain is made up of millions of these neurons, right? So when you see something, that's why you're able to judge the differences between things. When you see something, you have looked at, like right now, as you are looking at the screen, you can see a lot of things going on. So all the word for models, inspired, all those things are all coming to your brain. So you need a lot of neurons to receive all this information coming, and you process them within the neuron, and you bring an output. So you realize that in your brain, you have an input to your brain, then you have something that processes the information to the input, and then brings it out to the output. And that's how neural network is based on. That's how neural network is based on. So in the human brain, dendrites will receive signals, then the dendrites receive signals, the neuron will process it, and then goes through the axon as an output. So we just want to learn that idea and bring it to computers, right? So we'll say that we'll design something we call a neuron, and it will have several inputs, and then it will give me sometimes several outputs, or one output or two outputs, right? So we just want to mimic how the brain works, That's neural networks. Now, one thing is that how the brain understand with one thing is that you see your brain is able to understand not because you have only one neuron in your brain, you have millions of them. So the first neuron will try to understand what you are trying to say, what you are hearing, and the next neuron will try to understand the next neuron. So there are a lot of neurons, and all the information coming in are going to almost all your neurons within your brain, and then that's when you are able to make judgments, right? So we are not going to deal with only one neuron. So let's take that we have this neuron that is receiving information. Maybe you are smelling something, you are hearing something, you are You are seeing something. All these things will come in as input to your neuron. And we don't have only one neuron, a lot of the neurons. Just that you see, all the information that will come to almost all your neurons so that you make judgment out of all of them before you can give output. So in the same way, neural network always has an input, and we will have a lot of neurons within here that will be doing the thinking. Then we will have an output. So one thing you should know is that neural network has 3 layers. There's an input layer where the information will come in, and then the hidden layer where and we are calling hidden because it's where the information is being processed. And you see, one thing is that you don't worry about what is happening within your brain and what calculations going on within your brain before you're able to make decisions. But today we'll try and understand what is actually happening within your brain a little to see what actually goes on. But one interesting thing is that while the neural network is actually inspired by your brain, artificial neural network is just a simple part of your brain. The brain is so complex that neural networks cannot mimic it. Actually, what actually goes on within your brain after the dendrites receive information, some people think that some light is being ignited within the neuron and all that before some light signals will be sent and all. It's so complex that even neuroscientists are still looking at what is actually going on within your brain. But this idea, we can't actually model it well, but then we want to simplify that idea, and form something we call neural network. So we are just borrowing the idea that there's an input to your brain, there's a neuron that processes it, and there is an output. So in neural networks, we will have the input, and then we have the neuron. But the thing is that what is inside this neuron that will be doing the thinking is what even human beings don't understand yet, right? But we'll try to use some mathematics inside this neuron to try and understand the input coming in so that we can make an output. Now, the question we mostly have is, what is inside this neuron? When an information gets to your brain, what is inside this brain that actually do the thinking? Scientists modeling it is difficult for us. So one thing is that, let's see if I can get my pen here. Somebody is trying to write on my slides. So let's say within this is your neuron, information are coming in. What is actually happening within here? Now let's think of the idea that what is actually happening here. Let's just use a normal equation of a straight line, y equal to mx plus c. That the input that is coming, let's fit a line to it and get an output. So we realize that if you see this data right now, data like this, and you want to draw a line to fit this one, you know, from your brain, when you look at this now, you realize that you have to draw a line to fit this, right? So the idea of trying to know what is inside this neuron, we started with y equal to ms plus c as a line of best fits, equation of a line, that's regression. So we are using regression line, right? But realize that if the data changes to something like this, where we need a curve like this to fit it, normal straight line will not be able to deal with it. So it means that if you want to put something in this neuron, we can't just use y equal to ms plus c and fit it with a line, right? So, you know, in neural network, instead of using this y equal, I'm just making it in a very simplified way so that I get what I mean. Instead of using this y equal to ms plus c, we are going to use y equal to, okay, we are going to call y z. I'm going to say z is equal to wx plus b, where b, w is, we are going to call it the weight, right? And b is the bias, right? So the bias is just like your intercept, and then your weights are just like your gradients, right? So what it means is that the main idea is that we said that we are going to put a function z within the neuron so that any input that comes in, we may try to fit a line to it so that we get an output. But then realize that, as I said, it's not every data that comes in that we can just fit a line. So it means that we cannot just use wx plus b as the function within the neuron, right? As a function within the neuron. You have to think about something else. So some people have the idea that, you know, when you have data, don't even know where to, right? If you have data like this, right, where some data are here and you have some data here, right? You realize that a function like a sigmoid function, I'm not drawing it nice, will be able to fit this model well, like when you are doing classification. That's why we got to know something called logistic regression, right? Either the thing is 1 or it's a 0. So you see, when you have data like this, a normal sigmoid function will be able to understand when the data is here and when the data is here. But the question is, when the data becomes like this too, a sigmoid function too will not be able to deal with it. So what do we put as the function within the neuron, right? So let's look at it. So mathematically, y equal to wx plus b, which we are saying that we are trying to fit a line to almost all the data that comes to your brain. We are trying to see that it's a line of best fits, right? So one thing is that if we think of the neuron as having a line of best fit, even if we put another neuron to it to fit another line, when you have y equal to, I'll be doing some little mathematics with you today, and then you have this output and you go and put it in another y2, whose own 2 is another wx plus b. If you go and put this as x within this, you still get a straight line. So if we assume that within the neuron, there are some only weights and biases within the neuron, if we stick a lot of them together, no matter the number of neurons we put together, every day we'll be fitting a straight line to the data that comes in. And that will not be able to solve real world data where we have a lot of non-linearity, right? So we have something we call activation functions. These activating functions, no matter how many layers, so we are saying that without activation function, if you just use ws plus b, no matter how many layers you add up, the output will still going to give you a linear function, a straight line. So real world data too is nonlinear, it's curved, right? It's irregular and it's complex. So activation function will allow the network to introduce non-linearity. So we have seen that within the neuron, if we can still have this wx plus b and have something we call an activation function, f of z within the neuron, when an input comes in x, this x will try and have a line and then give it to a certain function that can bring curves within the model. We'll be able to understand how things work well, right? So this activation function is going to bring non-linearity to it so that we can know shapes, we can know the pattern within the data and all that. Now look at this. If we have this data, setting a line will do. But I see this data, you need a curve like this to separate these two data, right? But how can you, which function are you going to use to get this curve to separate this? There are various activation functions. So that's the reason why we need activation function, because we need some nonlinear curves, right? So there are various activation functions that scientists have found within some time. We have something called a sigmoid function. Now, I introduce you to the sigmoid function that is somehow like this. And if data is here and here, it's able to detect. But if the data is this, a normal sigmoid function will not be able to do. The sigmoid function is given by 1 plus e power this, right? So now we have seen that for me to have this curve, this sigmoid function, for me to be able to rotate this curve anyhow to get any curve that I want, right? So if I have a sigmoid function, I add another sigmoid in a certain shape, I'll be able to draw any shape I want to draw, actually. So every time before this sigmoid function, we are going to put wx plus b as a function into the sigmoid function. So let's call here z. Forget about the mathematics. I'll simplify things very soon. We are going to put this wx plus b into a sigmoid function so that we'll be able to draw curves, right? To be able to draw curves with them. Be able to draw curves. So sigmoid function is an activation function so that we can get nonlinear curves. Then we have something we also called tanh function. Tanh function too is also an activation function. So if you put wx plus b, so the input come, you try to fit. The thing is that if I have a sigmoid function like this, I can't move this sigmoid function around unless I have a line fitting it to be moving it around any shape I want, I can get with it. And if I stick a lot of them together, I can form any shape, right? So we have the sigmoid function and the tanh function. They are the mostly used, but I realize that there are some problems with this sigmoid and tanh function. So there's a function called ReLU. ReLU is a function like this, right? It's like this. It's like a normal straight line, but it's like this. This ReLU function, though it's like a straight line, but because of the curve, the bend here, you can form any shape with this by sticking a lot of this ReLU together. So let's say I can have this, I can stick another one like this and change the shape like this, change the shape like this. And at the end of the day, if I stick a lot of them together, I can form any shape. So if I want to draw somebody's mouth, I can stick a lot of these ReLU functions together, then I'll be able to draw them out. right? So every neural network, we are not going to use only one neuron. We are going to have one neuron, add another neuron, and all of them will have the activation function. As I stick a lot of them together, I can have any shape I want. I hope you got the idea of activation function. So something like this, a normal linear function will just draw this, but with a linear function and an activation function, you can draw any shape to separate data. So that's why neural networks are so serious and they are changing the world of AI, neural networks. So every neural network, as I said, will have this W plus B, WX plus B, where X is the input coming in. And then after this, we are going to give it to an activation function. And this function can either be a sigmoid, a tanh, or a ReLU function. It's called rectified linear unit, ReLU function. So that's when we want to understand what is actually happening within a brain, we want to use something we call a perceptron. So a perceptron is the simplest form of a neural network where we are looking at only one neuron, right? So looking at only one neuron, it will take an input, multiply them with weights and biases. So we can also consider the weights and biases. I have input 1, 2, 3. How much weight should I give to 1? Or how much weight should I give to 2? And that's the gradient of any curve, right? How much weight should I give to 3, right? And B is the intercept, right? Good. So every time my inputs come in, I will multiply them with W, which is the weight and the bias, before I give it to an activation function. And with that, so the activation function is the one that actually changed the world of neural networks, the activation function. So you see, the brain actually is doing plenty things, but we are just trying to say that inside your brain, we are having this. And that's not actually what is inside your brain, but at least we've been able to use it to do a lot of things. So mostly we don't use some functions so you can, in activation function, we don't use functions like, a sine wave that is going like this, right? If you want to, you have a data like this that you want to separate, and you have a sine wave, separating it with a sine wave, a Gaussian distribution line and all that. All those functions, mostly we don't use them as activation function because we need nonlinearity and we need functions too that are differentiable. Because as we go forward, I'll show you that these functions, at some point, we'll differentiate them. And if you don't have differentiable functions, you are not going to be able to achieve what you want to achieve. So that's why we have activation functions. So I'm sure you like activation functions now. So we have the sigmoid function is like this. It compresses numbers between 0 and 1. So no matter the input you give to a sigmoid function, if the input is 10, when you trace it, it is 1. When it is this, you trace it, you get 1. Or when it is here, you trace it, you get 0. When it is here, you get 0. So this sigmoid function, we use it for classification. If you want to classify things, one or two things, like you want to say whether something is yes or no, you are going to use a sigmoid activation function because it's able to give the output either 1 or 0. But the question is, what if the value is here? When the value is here, when you trace, you get 8. Anytime the value is greater than 0.5, you can consider it to be 1. And if it's below 0.5, I can consider it to be 1. So 0. So that's why the sigmoid function is very good. So anytime I'm doing classification, at the output layer of my neural network, I'm going to put a sigmoid function there, and it will be able to tell me whether the thing is yes or no. Then we have tanh function. That one compresses numbers between -1 and 1, right? You can also use that one to, just that we hardly use this tanh function in your output layer to say something is yes or no. But then, so as I said, you have your input layer, then you have neurons so this is the input in the hidden layer, and another neuron that will be the output, right? Good. So your input will come in, you give it to neuron, just that the hidden layer, you don't want only one neuron, you want plenty neurons within here, plenty of them, so that we'll give all the input to them. They all think using activation functions within here, which we can use as sigmoid, but hardly do we use sigmoid now. When neural networks started, we're using sigmoid within the hidden layer. But I'll talk about its challenge very soon. So sometimes we use tanh function. Tanh function to have some issues, so mostly now we don't do. And now we mostly use something we call the rectified linear unit, this function, right? This function, the nice thing about this function is that it's just given by the maximum of 0 and x. So anytime you have an input, if the input is a positive number, the ReLU function will just bring the same number out. But if the input is a negative number, so any negative number, it will say is 0. But if it's a positive number, you say it's 1. So this function its long and short is that it's the maximum of 0 and 1. So if I have negative coming in, that means that the maximum will give it 0. And then if I have a positive number, then I will say it's the same number. That's just how a ReLU function is. But I see it's saying that either 0 or x, but it's actually being a complex line that we can use to actually draw a lot of shapes by having a lot of neurons stuck together. Now, people are bringing in new activation functions with time. So as I was talking about more times ReLU, some are bringing something called leaky ReLU because some people say there are little issues with this ReLU and all that. But don't worry about them. Later in life, you understand other activation functions and how we use them. So what are the layers in neural network? You have the input layer, where the raw data, your input come in. Then we have the hidden layer. These layers contain many neurons, and it will transform the input into useful output. Then we have the output, and depending on what I'm doing, either I'm doing classification or regression, my output layer, I will decide which activation function I'll use in the output layer. Now let's look at the input layer. So let's say if you see this neural network, every time the first one here is the input layer. So I can have a lot of inputs, right? So maybe I have data, I have plenty data. The first one will come here, the second one, the third one, the fourth one, the fifth one. So I have plenty inputs. Now all these inputs, I'll connect them to a lot of neurons at the hidden layer. So now every input will go to every neuron within your brain. That's what actually happens. Every input, so that's why you have all the wires connecting all of them, right? So you take each input, you can draw lines to all of them. Take this one, draw lines. That's how we have it scattered like that. But one thing that I want you to understand is that every time the input layer does not have, it's just a placeholder. It does not have any activation function inside. So let's say you have input x1, x2, x3, x4. They just come and lie inside here. They don't go through any activation function. Now, as the inputs come to the hidden layer, that's when the activation function to try to see whether I'm drawing a line of best fit or I'm drawing a curve or I'm drawing this to separate a certain function or understand what is going on. And actually everything will happen within the hidden layer. So this is the hidden layer. So if I have this is my input. I know all this is my hidden layer. It's my hidden layer. Now the hidden layer, you can have a lot of layers. One nice thing about neural networks is the more neurons you are giving at the layers, the more understanding you want to understand the data, right? As I said, if you want to draw somebody's map with a ReLU function, one line like this, if you have another neuron and bring another line like this, you have another neuron and bring another line, you'll not be able to draw a map like that. But if you have about 500 neurons, I can put them like this together. I'll form a map. Nice one. So it's good to have a lot of hidden layers. But if you have too much too, the thing is that every neuron will process information and you're going to waste a lot of time because your model will be running, it will not be finishing, but you can have thousands of them to do the work for you. So let's say the hidden layer, can say hidden layer 1, hidden layer 2, hidden layer 3, can use different number of neurons within. So this is a layer, but then there are a lot of neurons. So you can use a number of neurons at any of the hidden layers. Then lastly, we have the output layer where the information will come out. So whether you are predicting it's a cat or a dog or something, but the output layer has activation function inside it. Input layer doesn't have activation. Hidden layer will have activation function, and output layer too will have activation function. But the activation function will have Wx plus b, as I've said, and that one will go into a function f of z. So to have a function z, and then this will come and enter into another function so that we can draw shapes, we can understand patterns within data. Good. So how to choose activation function for your layers? So the ReLU activation function should only be used within the hidden layers because you can't use that at the, as I said, input doesn't have any. So I'm talking more about the hidden and the output. You can't have a ReLU at your output because it's either giving you a 0 or x, right? So you can't use it to say it's yes or no most of the time. So every time you use the ReLU activation function in the hidden layer, then the sigmoid activation function should not be used in the hidden layer, but you can use it all right. When neural networks started, we're using sigmoid function, but I'll talk about its problem very soon, something we call vanishing gradient. So because of that, we don't use this sigmoid function within the hidden layer, right? So it's mostly used at the output. The sigmoid function is mostly used in the output when you are doing binary classification, or classifying two things. Talking plenty, right? Tange functions should not be used in the hidden layer because of something we call vanishing gradient, which I will introduce you to. But then you can also use it at the hidden layer sometimes, right? Good. But then if you are predicting something that you have to classify 5 or 10 things, right? You want to classify something as red, yellow, green, and all that. You can't use sigmoid. You have something called softmax activation function. So that one is able to give you a lot of outputs so that you look at the high probability one and choose that one. So you know some activation functions now, ReLU, sigmoid, tange, and softmax. Softmax always at the output activation function. So where activation functions applied, input doesn't have activation, hidden layers have, output layer has. And I'm showing that with this. Good. Now, you see, the main thing that actually makes neural networks so interesting is that inside here, as I said, we have a certain function, activation function f of z. This f of z, this z is wx plus b. These weights and biases are the most important part of the neural network. Because as I said, if I have a similar function like this, for me to turn it around, this weight and bias is what can come in to make sure it tends to become like this. If I have a ReLU like this, for me to turn it to become like this, I need this weight and biases. So if I'm drawing any shape or anything, I need to make sure that I'm choosing the right weight and bias so that I can turn around my functions and everything and get everything well shaped before I'll be able to draw anything. We are looking at image recognition. That's why I'm using drawing. But neural network is not only for drawing, it's for doing a lot of things, right? That's why I'm simplifying it in that side, right? So this weight and biases are the one that is going to tune your activation function and move it around. So in something that we do in neural network is that anytime you start, you see, this one will have a W. Let's call it W1, W2, W3. So all of them will have weights, W4, W5. This one to have W6, W7, W8, W9. There are weights within this. For me to get any shape drawn and all that, these weights need to, and then the biases, B1, B2, B3, these weights and biases need to be chosen so well so that I'll be able to draw any shape that we get. So in neural network, what actually happens is that every time you initialize these weights and biases. So let's say you say that W1 should be 1, W2 should be 2, W3 should be 0.4. You just initialize, you just choose any value for the weights and biases. And the neural network is able to learn with time to decide what the weights and biases should be so that the model will be able to understand the input data you have given it, right? So first, if you put the input in, it will go through, it will come as X values, go through this because you have initialized the W and W2, it will do some mathematics, right? And you can easily do the mathematics with what I've just shown. It will just find WX. So let's say W is 2. So we have X and then maybe B is 1. When an input X come in, the X will enter here. It will multiply by this, add the bias. And then after that, it will take 2. If you are using a sigmoid activation function, the answer you get, let's say X was 1, you get 3. 3 will become input here. And then it will calculate this and then send it to the next layer and continue like that, right? But then let's say the curve and all those things that you will get at the end of the day will not be able to fit the data well. So you have to come back and change these weights and biases, right? So anytime I'm passing the inputs and it's going through the layers for me to get my output, we call that forward propagation. It's just a term in neural networks. Forward propagation means I'm propagating the input through the network so that I get an output. But when I get the output, maybe what I'm predicting is not what I'm getting. So what I have to do is I have to come back and change the weight. When I'm coming back to change the weight, we call that back propagation. Back propagation. So we understand some terms now. So we are going to look at some terminologies in neural networks. So basically now we know everything neural network now. We're just going to look at some terms we use inside there. Forward propagation means we are passing the information. So let's say we have a so for this forward propagation, I'm going to take all the terms one by one: learning rate, batch size, iteration, epochs. Maybe if you have learned machine learning and all that, you have heard about some of these things. We want to simplify them. I don't know whether my time I'll be able to do all these within almost spending an hour. More time to go. Good one. Back propagation, let's take them one by one. Forward propagation, we are passing the information in, but realize that, let's say I'm predicting, yes, maybe I'm predicting something. Maybe I want to predict 10. I put in my data, my input 1 is say 2, my input 2 is say 3. I put in it to go through the weights and biases and activation function and all that. Then I predict 9. When I predict 9, the answer is not 10 if I compare it with my test data, right? If the answer is not 10, then means that I have to find the error. So we have something we call loss function in neural networks. So the loss function is just trying to find the error between what you predicted, the actual minus what you predicted, right? But most of the time, we don't want to just use the error. We want to use the squared error, but mostly we want to use the mean square error, the mean of the error that you are making, right? Anytime you use mean square error, means that you are penalizing the errors very well. So use the mean square error. So every time this loss function, after making any prediction, I will compare the thing was 10, I predicted 9. I find this loss function, and I know that I'm making an error of, say, 1. So I'll come back and update the weights. I'll change all the weights within the neurons, right? So when you are doing that, we say that you are doing back propagation. So you put in an input, you get a prediction, you compare it with the true value, then you check from your loss function how much error you have made, then you optimize your weight, you go and change your weight. When you are doing that, you are doing back propagation. Let's look at an example. Small mass, don't worry about the mass. I have an input X, but the output I'm expecting is 1.3. Maybe the weight, I'm just using only one neuron. The weight is 0.3, the bias 0.1. So the weight is this. I put in my X, my B, I get my Z. My Z is 0.25. I put it within an activation function. Here I'm using sigmoid. Ideally, I won't use sigmoid. I'll use a ReLU, right? Put that through an activation function, I get an output. The output, I was expecting 1.5, but then I got 0.56462. I will check it through the loss function and see that I'm making a loss of this. This loss is what is going to tell me how much I should go and change W1 so that I'll be able to predict well. So when you are doing that, you are doing back propagation. Back propagation. Now, how do you go and change the weights? We have a small function here. The new weight is the original weight you had minus a certain factor times the differential of the loss function. Don't worry about the differentiation. I just want to make a point here so that you just see what is going on. So how do I know? So let's say the weight was 10, or let me just use the weight that was. The weight was 0.3, was 0.3. How do I know that from the error I made, how do I know which value this W should become again? We use this small equation, right? So here is 0.3. Then we have a small parameter we call here alpha, and this alpha is what is called the learning rate. Talk about the learning rate. But one thing I want you to see here is that we have to differentiate the loss function with respect to the weights. But don't forget, but see, the loss function, the formula is not in terms of weight, it's in terms of y. So what it means is that before you can find the L, the W, I'm a lecturer, so I like maths. The L, are you following me? Are you here?
Yes, please.
Yes,
I hope I'm
please.
not talking in the air.
Yes.
Good. So before I can do the L, the W, I have to do the L, the Y first, because in terms of Y. Then after that, Y2 is in terms of Z. Then I multiply by the L, the Z. Then after that, Z2 is in terms of W. Before I would do times the Z, the W, right? So this is what is going to happen. All that I want you to see is you make the differentiation, you get a certain value, don't worry. Then you'll be able to know how much the new weight should be. Then you do forward propagation again. You go back and change the weight again. So you continue until you get proper weight that is able to give you proper prediction. That's all neural networks. But then you see, the reason why we multiply this by a small factor is that we don't want this is 0.3. We don't want the situation where from 0.3, we'll change it straight away to 0.1. Otherwise, we are just changing it too fast. Maybe 0.2 will be the good answer. If you just move straight to 0.1 like that, so you multiply by a small factor. So this factor is called the learning rate. You choose the value yourself. So most of the time, you use small values, 0.01 or 0.001. learning rate. So it's a hyperparameter. Hyperparameter means you choose it yourself, right? So this learning rate is the one that will help you. So let's look at learning rate. The learning rate is a hyperparameter that controls how much the neural network weights are adjusted. So you see, the loss function is, we are trying to minimize our errors. So let's say the loss function is given by this curve, right? So let's say first your weights are here, and suddenly, or let me say your weights are here, suddenly you want to check another weight and you move to another weight like here. But you see, the minimum point you want is here. So if you use a big learning rate, from this point, you move to a bigger point and you'll be away from the minimum point you are looking for, right? So bigger learning rates are not good. But if let's say if you are the weight you are using is a value here, if you use smaller learning rate, you will change the weight to another value here, change another value, small step, and by the time you realize you have zero error. So learning rates is just the step size that the model want to move in changing the rates little. So want to change the weight little by little, little by little. But the main issue we have is that I've seen that when I'm differentiating this loss function, I have to differentiate y with respect to z. What it means is that the activation function here, let's say if it's this, it needs to be the sigmoid function. It needs to be differentiated, right? And that's the main issue with using sigmoid function and tanh function as activation function within the hidden layer, because you have to differentiate this. So if you don't get a function that you can easily differentiate, but the main point is that this sigmoid function, when it is able to, you are able to differentiate all right, but after differentiation, any value you put in, you end up getting something around zero. So now see something. If you get this part to be zero, it means that this function you differentiated will be zero. 0 times your learning rate, no matter the value you choose, will be 0. It means that the weight will remain the same. So most of the time, if you use, so that's what we call vanishing gradient. The gradient, this gradient will be vanishing, it will be leaving, because the function that you are using as the activation function was supposed to be differentiated. When it was differentiated, you got 0 or a number close to 0. Even if you get 0.002, if you multiply 0.002 by the learning rate 0.01, you get 0.000 something, and it's almost 0. So that's why I'm saying that if you use those functions, the gradient will be vanishing. You understand vanishing rate now. So that's why most of the time we don't want to use sigmoid. The same issue happens with tanh. That's why we want to go with ReLU activation function within the layers. So you know learning rate now. So basically we are done with everything that has to do with the internals of neural networks. The rest of the things are just terms we use in neural networks. Now, one thing is that if you are training your data, let's say you have 1,000 data sets, and you want to train your model. So you have the neural network model, this 1,000 data set, or let me say you have 2,000 data sets, or let me say 1,005. Let's say you have 1,005 data sets, and you want to use, we have already explained that maybe you want to use 1,000 for training, 500 for testing. We'll talk about validation later. Now, this 1,000 data set that you are going to train the model means that you are going to go to your neural network. I've just written inside plenty, any of them. I'm going to put the 1,000 data sets here and bring it as input, right? So let's say the 1,000 data set, I have X1, X2, 1,000 like that. So you see, I have to pick the values and bring it as input and check the output. If I make mistake, I back propagate to change the weights, right? But you see, one thing is that we don't want a situation where this whole 1,000, we will put all of them within the training, the time we are training. If you put all the 1,000, what it means is that you will change the weights only once. So the amount that you take inside is what we are calling the batch size. The batch size. So if I'm using all the 1,000 inside, it means that the batch size is 1,000. I'm putting all inside, I'll change the weights only once, which is not good. So sometimes I can use a batch size of 100. It means that I'll pick 100 of the data and train. After training, I'll come back and change the weights and come and pick the next 100 and train and come and change the weight, pick the next 100. So it means that you are using a batch size of 100. And it's good you do your training in batches. So take batch size as, let's say, as I'm teaching you right now, for today, I'm giving you all the information. But in a normal class, if I have 6 chapters, right? So the whole course is 6 chapters. If I teach you 1 chapter and go home and come another day and come and teach chapter 2, that is the best way than to teach you all the 6 chapters at the same time. right? So you don't want to use a batch size of 6 like that, or the entire 6. You want to use a batch size of taking you one chapter, give you the information, take the next chapter, give you the information. So that's one good thing that you do in machine learning, in neural networks, called something we call batch size. Now, the thing is that if I use all the 1,000 and I give all the 1,000 within, as I said, I'll back propagate only once, right? Anytime I put all the input data inside, we call that an epoch, right? It's just a name. It's not anything. So when you go and see all these terms and AI people are just talking about them, it looks strange, but they are not anything. When I give all the data to it, when all the data goes through the neural network, I say I've done one epoch. So if I give all the 1,000 at the same time, that is only one epoch, right? But then if I split it into 100, 100, 100, right? And when I give the 100, I've not covered the epoch. Epoch is when I've given all the data to the model. So though the batch size is 100, I have to do a lot of about 100 times 10, right? I have to do it 10 times. We have 1,000 data set. So if I give 100 batch size, another 100 batch, another 100 batch, another 100 batch, I have to do 10 before I will cover one epoch, right? I have to do, like, let's say if there's 6 chapters, I have to cover 6 chapters before I will teach one course, right? So the epoch is you have finished the course. So when you bring in the data, so if I do it chapter by chapter, it means that I'll do it 6 times, but one time that I've given you the information, right? So in machine learning, most of the time, we don't want to, in deep learning, we don't want to give the information only once. Like your lecturer teach you the whole chapter. Can you imagine that he comes again and teach you the whole chapters again, and teach you the whole chapters again? So sometimes we use an epoch of, say, 5. It means that we'll give you all the information, come again, come and give you all the information, come again, come and give you all the information, so that you will learn well and understand things, right? So the epoch is when I give you all the data. But if I have 100 batch sizes, it means that I will go 100, go 100, go 100, go 100, 10 times before I cover one epoch. But if I give all the 1,000, I give it once, then I get one epoch. If I use a batch size of 500, it means I give 500. I've not covered an epoch yet. I give the next 500, then that's one epoch. So it means that we have 2 batches in an epoch in this area, right? But we have something called iteration. Iteration is anytime I put an information and I come back and come and change the weight. So let's say if I'm using a batch size of 1,000, it means I'm going to do only one iteration because I'll give it once and I'll come and check the weight once. If I'm using 500 batch size, it means that I'll give the 500. It means that that's one iteration. Then I give the next 500. That's the second iteration. So I'll do 2 iterations before I cover. I hope you are following, because I'm using a batch size of 500. If I'm using a batch size of 100, I mean I'll give the 100 10 times. It means I will do 10 iterations before I cover an epoch. So batch size, the size of data that you give, anytime you give a batch, is an iteration. If you give all the batches, you get an epoch. Good. I hope you understand. The video will be there, so you can go and read it anytime you want. So I've covered forward, backward, learning rate, batch size, iteration, epoch. And I've spoken about vanishing gradient too already. So let's say you have your batch size. So in deep learning, data sets are usually divided into smaller subsets called batches. And iteration occurs when each batch is processed. Anytime each batch goes, let's say this batch goes, one iteration. The next batch goes, the next iteration. The next batch goes. So when I finish the batches, one epoch. Just as I say, want to train more. So after one epoch, I come and give the batch again, batch again, batch again, batch again, batch again, second epoch, right? Good. So let's see a batch size of 1,000. It means that I'll have one iteration per epoch, only one iteration per epoch. If my batch size is 200, means that 1, 2, 3, 4, 5. I'll have 5 iterations for one epoch. And then if it's 100, I'll have 10 iterations for one epoch. Can go and read epochs. And I've spoken about vanishing gradient. It's a serious problem that occurs during the training of neural net. As you are training, you want to go and adjust weights where the gradients that are used can get to 0 or vanish. So this makes it hard. So you see, most of the time, the weights are not changing. It means that nothing will be happening. The training will not be going on. Even if you bring one batch, bring another batch, the weights are not changing. Nothing will happen. So we don't want vanishing gradient. That's why we have to choose the right activation function. And that's why we want to go with ReLU activation function, because ReLU, you have 0, x. So when you differentiate, you get 1. So definitely there's no way you are going to get the ReLU function to be giving you But sometimes when you have negatives and all that, you can get 0. But sometimes ReLU can have an issue. That's why some people are bringing something called leaky ReLU and other activation functions that can deal with such issues. But every time use ReLU in your activation function. So this is the issue of vanishing gradient. The sigmoid function is like this. When you differentiate, it becomes a function like this. Any value you put will be getting 0. Any value you put, only small amount of value will not give you 0, but it will give you 0.00 something, which is not good to have that as activation function within the hidden layer. Good. Any question on neural networks? So now you know neural networks, right? So almost every deep learning model is going to be based on this neural network we have explained. Everything. So I can talk about CNN, and CNN is going to be based on that. Let me check if anyone has question for me in the comment section. Let's just have some 1 minute of question. Do you have anything for me?
Yeah, hello.
Yes, sir.
Yeah, good evening.
Yeah, good evening.
Yeah, thank you for the presentation. I'm a bit confused. You talk about the hyperparameters,
Yes.
where you talk about W is changing.
Yes.
When you are carrying on the work, at times you change the W in order to get the perfect model.
Exactly.
Yeah, so I would like to know, what if maybe you are working on a stuff and that W is fixed? Are you going to change it maybe for specific material, and the W is fixed for that material? Are you going to change that number to fit the model that you're trying to predict?
Yes. So W will always not be fixed, right? So the W is inside the neuron. So if you have materials, maybe different types of alloys and all that, these are materials. And the W is not about the material type or anything. The W is the neuron, your brain, trying to understand the material. Which type of material is this? So as you are, so see yourself adjusting your brain as you are trying to understand, is this a polyester material, or it is this material? So as you are thinking like that, you are changing your weights. You are changing your thinking patterns, right? So the material will be separate, but your weight is your thinking pattern. So that's why the weight always need to change. And it will change within the model. It will not change as in with the material. So as the material comes in, the weight will change to understand what material it is. Are you getting the concept?
Yes, I'm getting the concept. So if the W is always changing,
Yes.
regardless. Okay.
So it will change till you fully understand that this is the material. Then I stop changing.
Okay.
Good.
It's
We'll
clear. It's
explain.
clear.
Good. We'll explain more of that. So now let's go to image recognition. So with all the neural networks I've spoken about, how do we detect that this is someone's face? This is a cat. This is a dog. This is this. This is this. We are just going to have the same thing. Neurons are going to be there. You are going to have hidden layers. You are going to have output layers. You are going to use activation functions. Just that convolutional neural network does something we call convolution. And that is actually, I can use normal neural network to detect anything, right? Can use normal neural networks. But the thing is that it comes with a high cost. And in machine learning and AI and deep learning, when you talk about cost, it's not money. Sometimes it leads to money though, because as you are needing more hidden layers and more neurons, the thing have to run a lot. You have to change the weights a lot of time. You need big computers. You have to buy them, right? So cost can be monetary and all that. So using normal neural network to detect faces is possible and all, but then someone came with a nice idea that we can detect this thing easily without trying to do a lot of weight changing and a lot of neurons and all that. So brought something we call convolutional neural. So you see, it's a neural network that we're going to do something called convolution. So now, before this convolutional neural network, we had something called computer vision, where we wanted computer to be able to see something and understand. And how does your computer know that this is a cat, this is a dog, and all that? It's actually using something called computer vision, where you sense an image, and based on the image, you can decide to do some things to understand how the image is like. right? So CNNs, they are just a special type of deep learning, mainly used for image recognition and video detection, video classification, and all that. So unlike the normal neural networks, CNN take advantage of the fact that every picture, when you have a picture, a picture is like when you take a picture like this. Actually, your picture is broken down into pixels. You can draw lines within your picture. It's lines like this. And every box within the picture is called a pixel. So every box within a picture is called a pixel, right? So we can use this idea of your image being pixels to do something. And that's what we want to look at using convolutional neural network. Now, before convolutional neural network, I just want you to just look at what do you see? This is a rhetorical question, do. But you see, what do you see in the bowl there? Quickly, you can see some apple, you can see some orange and banana and something. But I see, to make a computer see this thing is a serious task. And that task is what we are looking at right now. How would the computer know that this is a mango and this, and it's in a black bowl? You see, in the olden days, this was a serious thing to do. So some people started learning about how your eye sees and gets to the cornea and the cortex of the eye and gets to your brain, the neurons and all that, before your brain will be able to understand that it takes a lot of things, right? So that's where computer vision started, how computers will be able to see and interpret and do things. Now, earlier on, before I can know that there's a mango inside and the orange inside and all that, engineers have to sit down to craft something we call to know the features within this. As I started, I said deep learning, most of the time, you don't need to know the features. Deep learning is able to understand the features by themselves. So that's why deep learning started changing the idea of computer vision, because an engineer have to sit down to see what are the things inside here so that I'll be able to design something to detect this thing. Let's say I have an image where there is one inside there. What it means is that all here will be white, but then I'll see colors here. There will be colors here. There will be colors here. There will be colors here, like this. But all the other places are white. So as an engineer, when I sit down and I want to detect whether this is one or not, I have to look at something I'll be introduced you to call something we call filters. So in the olden days, engineers have to sit down to design this filter so that they go and use this filter to multiply this image. When you are multiplying the image, a filter, so the filter to have numbers within, right? Maybe here is 2, 3, 4, this. So this number one mostly is changed into pixels because it's an image. Now, the thing is that every color has a number. That's what I want you to know. Every color has a number. And these numbers are mostly between 0 to 255. And there are more electrical reasons and computer reasons why you use 255, but these are just numbers, right? When you have this image first needs to be converted to pixels. So I have to change it to pixels. How do I change to pixels? I have to know the color at every box. So I have to divide this into boxes. Like this, box. And every box, I have to know the color there. When I know the color, I'll put the colors number. So I have to also do, this is my pixels. I'm just converting the image to pixels, right? So this color is white. White is 255. Come and put 255 here. This place is white. Here is 255. 255, this. But where maybe, let's take that this is a black color. Where there's black, so there'll be some 0 here, some 0 here, some 0 here, some 0 here, some 0 here. All the other places will be 255 or a different shade, depending on the colors there. So this is how the picture will look like. So have you seen that there's 0 here, 0 here? At least I'm getting my one. And that's how I'm able to do. Just I see, because I'm using my eye. That's when I got to know that there's 0 here, there's 0 here. I'm getting a one. How will I be able to do that? I need something we call a filter. Let's say I make this filter. Let me use something like this. And like this, and put here 1, 1, 1, and put here 0, 0, 0, 0, 0, 0. If I come and multiply this filter with these pixels I have right now, right? I'm coming to talk about convolution very soon. I will multiply, I'll put this filter on this image step by step within the image. When I do that, you see the number, this time 0 will get to 0, this time 0 will get to 0, this one 0. So only the places, and here I'm using zeros. Let me use numbers. So let me just say the number here is 111. Just to make a point so that I get what I'm trying to see. When you multiply, they realize that everything here will change to zeros. Only here will have numbers. Ooh. Only this part will have numbers. And because only this part will have numbers, I'll be able to now know. So you see, I have to specially design and make sure that the 111s are here so that I'll be able to detect. If this number changes to 2, I'll have to design a filter that will be able to detect that. So engineers have to sit down every time and design filters to be able to put on the image to notify how, notice how the number is within the text and all that. That was too cumbersome and tired, a lot of work to be done. So that's why convolutional neural network does that automatically for us, because I don't need to understand where the filter, the numbers need to be. Now, this filter are just the weights we have been talking about. They are just the weights we spoke about in neural network. Just that here we are defining the weights in just a nice way. Take your pixels are now going to be your input, X. We are going to multiply this X by the weight. So in convolutional neural network, most of the time, the bias, we forget about it. And it's hard to use the bias, but most of the time, forget about the bias. So we are just going to do Z as WX. So the filter are just going to be the weights. But here, have you seen the neural network? Every neuron have weight. Every neuron have weight. But here we are just going to use only, let's say, a 3x3 filter, 3x3 weights, so that we will be adjusting these weights within here till I'm able to notice a number within there. Right? So that's one nice thing about convolutional neural network, because you're not going to use a lot of weight and millions of weights and all that, which will require big computing power and all that. So I use a filter. And now, what am I going to do? Let's go to. So conventional way, people have to design. So if let's say I have a number like this, and the number is at the edge here, I have to design a filter, an edge detector to know that it's here. If the number is a horizontal, it's here. I have to make sure that I design a filter to detect it there. So I have to design edge filters. If I want to know texture, I have to design a filter to know the texture. That was too much work for computer vision. So neural networks. So the limitation of traditional computer vision is that it requires domain experts to choose the right features. Because as I said, an image, you don't know the features there. So you have to, for you to know that this is the feature there is 1. You have to decide by yourself. And people have to sit down to do that. It was too complex and the performance dropped, right? Good. So CNNs are able to learn automatically and adjust the filters I'm talking about so that they will know the pattern within the data and understand the complexity within the data. It will be able to know by itself whether the number is at the edge or in the middle or anywhere, right? That's one nice thing about convolutional neural network. So in convolutional neural network, step 4 and step 5 are the things we know in neural networks already. Fully connected layer. It's about neurons, a lot of neurons all connected, and then we have your output all connected. So we know all this. Before the input here, we are just going to do some few things within here before we'll give it to a normal neural network. And this side is the convolution side. We're just going to do something called convolution here, then we'll give it to a normal neural network, and our work will be done because we know neural network already. So how are we going to do the convolution here is what we are just going to go through. So the input will come in, all right, go through something we call a convolutional layer. And at the convolutional layer, we're going to use something called filters. We already know activation function. And then we are going to know something we call feature map. This thing will occur within here before we'll give it, and then we'll do something we call pooling before we'll give it to a normal neural network to continue the work. That is a convolutional neural network. So now let's say let's look at the input layer first. You have an image. You want to know whether it's a cat or a dog, whether it's a human being or it's not a human being, whether it is a tree or not a tree. What do you have to do? And mostly we call that image classification. Sometimes we use classification, image detection, object. But most of the time when I talk about object detection, it means that I want to know the main thing going on within there. I want to know the name of the thing, right? If I have cat and dog, and I want to know whether it's a cat or a dog, right? I don't need to mention that it's a cat, or I don't need to mention that it's a dog. I just have to say it's a yes or a no. right? And that one called that image classification. And basically, that's what we are going to look at today. But most of the time, if you want to know the name of the thing, so let's say you see an image, you'll be able to tell that it's Obama or it's not Obama. All right. So we are doing image classification. But if you want to really say it's really Obama but it's not Trump, then, or President Trump, then you have to do object detection. And object detection too is another story. Another time, maybe if you have time, we will look at object detection. But let's look at the basis of everything. Convolution. In my time, I'll be able to meet the 30 minutes. Hey, we have to run simulations. Let's see your image. Number one, let's start with the image. So let's see your image here. This is a car. We want to know whether this is a car or a bus or a truck or a car, a cat. You know, your eye, as soon as you look at it, you knew it's a cat. But in a normal deep learning model, you have to go through all this process before you to know whether it's a cat or not. So first of all, this car will be broken down into pixels, as I said. Into pixels, this car will be changed to numbers. Here will be a white number, white number. Here will be a blue number, blue number. Here will be a white number. So the car will be drawn within as numbers for you like that. So when we change it to pixels, we will get something we call filters. The filter is just going to multiply the image. When the filter multiply the image, you will get another matrix, because the pixels have become matrix. When I multiply that by the filter, I'm going to get another matrix. That matrix we are calling the feature map. Now, when I'm multiplying the filter values with the image values, we call it convolution, just a name. Mathematics, when you are doing dot product, you say you are convolving, right? Dot product. You are going to do dot product. So when you do a dot product of the image, the filter together with the image, and as I said, the filters are the weights, just a box of weights, that's all. And multiply that, we are doing convolution. So we will do convolution. After the convolution, we got something we call something we get as a feature map. Now, this feature map, I'm going to talk to you about something we call pooling. I'm going to do something called pooling. When I finish the pooling, I will get a lot of numbers, then I will arrange the numbers and give it like this. We call it flattening. I'll flatten the numbers and give it to a normal neural network to continue the work. And I'll put a softmax activation function. As I said, you see, here I'm doing a lot of prediction. I can't use sigmoid function. So I'll use a softmax activation function here. So the output that comes, so let's say the probability that this is 0.8, this is 0.1, 0.02, 0.03. So the probability that it's a track or a cat, I make this one 0.1 and 0.02 because it can be a track. So looking at softmax will change this one to probability. So the one with the higher probability will tell you that it's a car. That's all that is happening in convolutional neural networks. So the input is changed to pixels. We will use filters to multiply the metrics of the pixels, get something we call a feature map, do something we call pooling, then arrange, or we will flatten the numbers we have, send it through a neural network. We call it the fully connected layer, and then we'll be able to make predictions. So this is the layers we are going to go through one by one, right? Let's look at the input layer. Every image are numbers. When you take a picture, the pictures are stored as numbers. So your input is always an image, and your image is like this. So there is a height of your image and then the width. Just that there's something called channel. So normally when you take a normal picture, which is black and white, the channel is 1. I'll talk about channels later. The channel is 1. This is when it is a black and white picture. Now, if you take a colored picture, because it's colored, right? How do we change colored numbers? So if the thing is black and white, we will use something we call grayscale numbers. These are numbers between 0 to 255, as I explained. Every color, so if I take a black and white image, black has a number, gray has a number, deep gray has a number, white, the intensity of the white, dark white, different colors, every color has a number, right? So we have something called a grayscale. Every image will be converted straight to grayscale, and then the colors within there all will be given numbers, right? But if it is a colored image, like your face, let me show I'm here together. Let me just show you. If this is your face, right, which is a colored image, every color can be formed by using red, green, and blue. So we call that RGB. So what it means is that if I want to change your face like this into pixels, I have to know what's the content of red, what's the content of green, what's the content of blue. So the content of red will tell me the numbers. So the amount of red here, the amount of red here, the amount of red here, all will be put as numbers within here. The amount of green. So what it means that if it's a colored image, it will not just be a height and a width image. It will be a three-dimensional image like this. Let me see whether my technical skills work. So there will be a red pixel part, a green pixel, and a blue pixel. All this, when I put a number here and the number here and the number here, I'll get a color here. When I put a number here and the number here and the number here, I'll get a color here. You can go to Photoshop. You go anywhere. Anytime you are selecting colors, when you select the color, they will let you know the amount of red, green, and blue inside. Every color can be made with green, red, green, and blue. So call it RGB. So anytime it's a colored image, it will be a 3-pixel image. So we say it's a 3-channel. So it's not just height and weight, but then it will come with a channel, which is 3. But I won't deal more with colored images today. Let's simplify things with a normal black and white image. Good. So if it's a black and white image, so depending on how many times you divide this, so if I divide it 28 by 28, it's a 28 by 28 pixel. And the thing is that, see, the more pixel you have, you are opening the image. Or when you reduce the pixel, you are shrinking. So when you are trying to compress your image and all that, you realize that the beauty goes down because you are reducing the pixels, right? Good. So that's why every time camera, you want the one with the higher pixel so that to be able to show the images well. So if I divide 28 by 20, so we say it's a 28 by 28 by 1 because it's a black and white image, right? Only one channel because the pixels will be only one matrix. But if it is RGB image, a colored image, maybe it's a 32 by 32, it can be any number, right? It's a 32 by 32 image. We'll have 3 different ones. So we'll have 3 channels. So it's a 32 by 32 by 3 channels, right? Now, whether red or green or blue, all of them have a number between 0 to 255, right? So when you put them inside there like that, you form matrices, and the matrices now become your image. Each pixel is normally normalized. So I'll talk about normalizing the pixels and all that later. So let's say, have you seen this picture? How do you know it's 8? This 8 is broken down into boxes. Now, if you see the image here, can you see the 8 within? Because you see every color, the black at this point is 0, 0, 0. So have you seen the numbers? So every place with the colors, the numbers are there. So every pixel every time is changed to numbers like this. So you have this matrix there. Interesting. Now, one thing about Python and all those, that as soon as you import the image using TensorFlow and all those things, you'll be able to get the thing converted to numbers already for you straight away. You see, because we are using our eye, that's why we can see 8. But you see, computer don't know that. You have to see these numbers. Now, what are we going to do with these numbers? This number is the image. We are going to have something we call filters, which is the weights. So now, one thing is that, as I said, these weights, first, somebody have to sit down to determine the numbers within. But now, let me use a 3 by 3 filter. So maybe I can just put 0, 1, 2, 0, 3, 0, 5, 0, 6. I can put any number. As I said, we initialize the weights anytime. So we just put any number within here. Now, what we are going to do is that I'm going to come to this image and I'm going to take the images 3 by 3. So have you seen I pick 3 by 3 within? So this entire image, when I pick a portion of it, it's called a patch. These are just terms we use in deep learning. So I'll pick a patch and I'll multiply it by the matrix. When I multiply, I'll get an answer, only one answer, because I'll do dot product. 0 times 0, 1 times 2, 2 times 15. Hey, this one is more than 3 by 3. So I'll do 0 times 0 plus 1 times 2 plus 2 times, so it's called dot product. When you are doing that, you are doing convolution. The answer I'll get, I'll come and put, so I'll draw another matrix like this, and come and put, maybe I get 10, I'll come and put the answer here. Then what I will do is that this filter is what I came to put here. Yeah, that when I put on it, it will cover the numbers. That's why I didn't come and put on it. Then I will move the filter now to another 3 by 3. But you see, I will move only one step. The number of steps you move is called a stride. The stride. So if I move only once, so that now I'll take 2, 5, and 0, this matrix. To be good, let me use different colors so that I know this well. So let's say first I take my 3 by 3. When I finish the answer, I get 10, I put it down. How do I know the next number? I'm going to, let me use yellow. Oh, yellow people will not see. Blue. I'll move the filter by this and take the next 3 by 3 and do the multiplication again. So because I move only once, I will say the stride is equal to 1. Somebody can decide that he wants to, because you see, the more if you are moving one by one, like it can take you a lot of time. So just that the thing is that it's good to move one by one, because when you are doing that, you are capturing what is inside the image well, right? You are capturing what is inside the image well, because as you do the multiplication, you get numbers, and every number has a color. At the end of the day, when I convert all that numbers in terms of colors again, I'll see a certain image. That's why I'm saying that it's very important, right? You choose the number of stride if you want to use a stride of 1. So when I pick any portion, it's called a patch. So I take a filter, I put it on a patch, then I slide. Now you know the terms of CNN, right? I slide. Can slide by 2. If I slide by 2, then when I finish, I'll slide again. I'll slide again. I'll continue sliding until I capture all the image. Continue slide and move around so I cover the entire image. Now, you get all the answers you get by doing the convolution. So you see, as you are doing the multiplication, you say you are doing convolution, you add them, you put the answer. You come and put all the answers inside here, and this now you call it a feature map. A feature map. And basically what you have done here is to multiply X by W. That's basically what you have done with the filter. Forget about bias most of the time, because to make the thing complicated. So most of the time, CNN forget about bias, but you can bring it. Good. Can you see that this is actually someone's face? But someone's face in terms of pixels is like this. Your eye is somewhere here. So your eye has a certain color. But you see, black is 0, but maybe the intensity of the blackness will be, say, 10. You say 13. So depend on the grayscale numbers, right? So all this, your image, your face like this will change to these numbers. And these numbers will now become only numbers now. Then I'm going to look for a filter and come and put on a patch. Move and slide by 1. Move and slide, slide and slide, and get a feature map. Nice one. Now, if it's a colored image, that's another thing, right? Because now you have 3 pixels, 3 different pixel matrices. So when you choose a matrix, you have to choose a 3 by 3 matrix too. 3 by 3 filters. Now, these filters, sometimes we call them kernels. So most of the time, sometimes you want to use kernel or filter, maybe you may understand. Sometimes, you see, in AI, we just use our own terms so that people don't understand some. So kernel or filter. So that one, you have to get 3 by 3 filter so that this filter will be convolving here. This filter will be convolving here. This filter will be convolving here. Just like I see when we finish, the answer this one. So at the end of the day, I'll get a matrix, an answer matrix, I'll get a feature map. Just that when I finish, the value here will be added to the value here to get a value here. The value here will be added so that I'll get only one feature map after the convolution. So I'll use a 3 by 3 filter, all right. But after multiplying, I'll add all the numbers and then I'll get only one feature map out of it. Right? Good. Ideally, in every neural network, it's good you don't use only one filter. Because, as I said, a filter may be able to detect the numbers here. Let me use my red now. Another filter may be able to detect the edge, the curve here. Another filter may be able to detect here. So most of the time, let's say with this image, I can use about 32 filters. Each of them will have their own numbers within, then I'll multiply, then I get a feature map. Then I use another filter and do multiplication again and get another feature map. So let's say if I use 32 filters, I'm going to get, after convolution, I'm going to get 32 feature maps. So that I'll be able to detect everything within the image. But if it's colored, as I said, This apple that you see there will have a red colors, green, and this. When you put this number, and this number here, you get a color here. When you put this number together, you get a color here. So this image is broken down into pixels, become like this. If you have a cut like this also is broken down into, because it's colored, it will give you 3 matrices. It's a 3 channel. So I'm not using to say 3 channel. These 3 channel have to get 3 channel filter to come and multiply and get at the end of the 1 feature map to bits. So convolutional layer, this is the most important layer of CNN because that's what is a little different from the normal neural network. A filter, which we are calling a kernel, most of the time we use a 3x3 filter. If you use a big filter, you will not be able to capture some things within the image. If I use a filter like this, here I will not be able to capture what is really inside here well, right? So most of the time I use small filters, and most of the time I use 3x3 or 5x5. Those times I used to use a lot of 5x5, but now most of the time 3x3 filter. We will slide it, but now in neural network, in convolutional neural network now, we'll not be saying we're sliding it. We'll stride. We'll stride around the image, and then we'll do a dot product within convolution on every part. You know the terms now. And at the end of the day, we'll get a feature map. Right? Be a feature map. So look at this. Let's say you have this image. I take this patch, and this is my filter, and I multiply it with the patch. 0 times 9. So see the calculation, 0 times 9, this, and I get 16, I come and put it here. When I finish, I will slide by 1. Do the multiplication again, come and put the answer here. Come and put the answer, come and put the answer, come and put the answer. Come and put the answer. I don't want to go into the mathematics well, because most of the time, if I have a filter of say 3x3, and I'm 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then my image is 5x5. If I have my filter size, I know the size of my feature map. There's a small formula that you can use to calculate that, right? Good, you know the size. But the thing is that when you do the calculation, you come back to that size. So don't worry for now, so that I don't do a lot of math with you. Good. So see the convolution going on there. I take this filter, come and take this patch, multiply, come and put the answer. Take the patch, multiply, put the answer, multiply, put the answer. Then I get this feature map. This feature map. And I just designed this. I just use Python to just do this. Let me play again. Oh, it won't play again. Just wanted you to see how the, hey, if I go again to our discard all the, let me keep all the writings. So have you seen how the patches, the filter is moving around, striding 1 by 1, and then to change all of them to these numbers, right? Now, so we have just done W. Come back. You have just multiplied the weights, and when you have the slide later, use your phone and go to this. Take a picture of this. It will lead you to some image doing patching, as in doing convolution, so that you see a visual one. I just put it there for your visual. Somebody can use his phone to take a picture right now. You see something, but don't worry about seeing something now. So let's say you have an image. So this is what is going on within any image. If it's colored, I don't talk about colored plenty today. It is colored. The red part, the green, the blue will be taken. You have to get a 3x3 filter. So the filter now become a 3x3. It's a 3x3 filter, but to have 3 channels. So you see us writing something like this, right? They will come and multiply. By the end of the day, you come and get a feature map out of it. So now you know what a feature map is. Now, the convolution is done, as I said, we don't use only one kernel or one filter. We use multiple filters because, and then I said the output of the convolutional layer will give us a feature map. Now, the reason why we are using different filter is, as I said, different filter will let us know the shape, will detect different shapes and different edges within the image. I've defined what a filter is. It's a small matrix of numbers, random numbers, and actually the weights. It slices or it convolves across the image pixels by pixel. At each position, the filter will do a dot product. The resulting thing is a feature map. And then each of the filters will be able to know which side is the vertical side of the image, which side is the horizontal side of the image, what is the corner of the image, what the texture of the image. And when we do that, we find the shape, right? So the reason why we use multiple filters is that a single filter can only detect only one feature, only one shape. So we use dozens and even hundreds of filters every time so that we can have a feature map bank. So look at something like this. You have an image, you put the first filter, you'll be able to detect these edges like this. You put a lot at one layer, as I said, we just did convolution. The thing is that we will not finish. We'll go and do another convolution. I'll talk about it again. So we'll do the convolution step by step. And the more you do it, you'll be able to detect images. I've seen that at this step, when you do the convolution, you'll be seeing pictures like this. But then as you do more convolution, that's when you start detecting people's eye. So when you are going deeper into the convolutional layers, so we have a convolutional layer, but most of the time we not use only one convolutional layer, like how we don't use only one hidden layer, right? So convolutional layer, you can have one convolutional layer, another convolutional, but we don't use plenty like that, maybe 3 convolutional layers. So we get a filter, filter, multiply, and get a feature map. We take the feature map, multiply with new filters, and get another feature map, multiply with new features, so that we'll be able to detect people's faces. And numbers will detect the faces, you'll be surprised. You'll be surprised. So the early filters will know only edges. Middle filters are the next. So this is convolutional layer 1, convolutional layer 2. And in this convolutional layer 1, we are going to do a lot of things. We are going to do convolution. We are going to use a filter. And then we are going to do something called pooling. The pooling is what I've not spoken about yet. So we're going to do pooling. I think it's only pooling left now. So do pooling. Then after that, we take it to another convolutional layer and get new filters so that we'll be able to detect people's eye. If it's a car, we can know the hues well. So as we go deeper with more convolution, we'll be able to detect people's faces and all that. Now, one thing is that after multiplying the image with the filter, like all the things I'm showing here, as you get this feature map, most of the time, this feature map, we don't just go and use it. We have to pass it through an activation function. So as I said, you have just done WX, pass it through an activation function f of z before you can use it for anything. So most of the time when we are explaining convolutional neural network, we hardly talk about the activation function. But one thing is that the activation function is the one that will be able to get this shape. This shape. So actually, we can use this to form a circle by putting a lot of them together, right? Good. So after this one, it will go through an activation function. So let's say if you are using ReLU, what will happen is after this feature map, but most of the time, as soon as we do the filter multiplication, we do the activation before we go and put the feature map. But in CNN, we hardly talk about the activation, right? But then I want you to know that it's actually going on. So what will happen is that any number now, so this one will give us new metrics. Any number that is positive, the 12 will be there, the 8 will be there. This negative 7 will be changed to 0 because of the activation function, because using 0 or the max. If it's a positive number or the x, if it's a positive number, put the number, but if it's a negative number, put 0, right? So it will change all the negative numbers to become 0 within the feature map. So after convolution, we do, after taking a filter, we go to a patch, do convolution. After that, I say I'm repeating it several times so that you get to know. After that, you get a feature map. But before the feature map comes out, you go through an activation function so that all the negatives are changed to zeros. And then you have a nice feature matrix. Good. So I've spoken about the activation function. So either use ReLU or sigmoid or softmax, but as I've already explained, use ReLU. So if you have this feature map, we're going through the activation function, all the positive 15 will come, 10 will come, 20 will come, negative 10 will become 0. So we go through the activation function. So this is the final feature map. But most of the time, we don't talk about it. We just bring the feature map, right? But need that. So a feature map is just the output of a filter multiplication. It shows how and how strongly a feature is. So that's why it's called a feature map. A filter trained for, so if you have so because you define a lot of filters, one of the filters will be detecting vertical edges, horizontal edges, and all. So that's why you need to use a number of filters. At the deeper layer, you can know somebody's eye, can know somebody's face just by doing multiplication with W and then passing it through activation function. Now let's talk about pooling. Now you see, when you finish our activation function, when we do convolution and then do our activation function and get our feature map, we'll get a big matrix. Now this big matrix will have the size is big. We don't want to take all these numbers to a normal neural network. Otherwise, we have a lot of inputs to the normal neural network, right? That's to the fully connected layer. We don't want to take all of them, so we want to do something we call pooling. We are going to pull the most important part of the image. Let me use a diagram and you understand. So let's say this is the feature map I got, right? Now you see every pixel is a color, right? So now in pooling, you have to decide your pooling size. So let's say I want to use a 2x2 pooling size. I will explain. What means that when I take my feature map, I'm just going to take a 2x2 matrix out of the feature map, and I'm just going to do pooling. By pooling, we have two types, and mostly we use this max pooling. Let me talk about that. I'm just going to pick the highest number within the 2x2 matrix and come and put it here. Now, somebody says, if you do that, are you not distorting the image? Actually, you see, these are all colors, right? So you see the numbers we are trying to detect is a black background with a white point. So the white is 255. So the place that has white is where the number is actually. So this may be just some color background we don't need. But as soon as I pick the bigger number in, I'm actually picking the image at that spot within the pixel. So I hope you get the idea of pooling. So you can do max pooling by picking the maximum. So you have to define the size of the pooling you are doing. Most of the time, I want to use 2x2 pooling, right? So this feature matrix, I just take a 2x2 matrix, pick the highest number. When I'm doing max pooling, I make it 80. Here I pick 97, come and put. Here I pick 25. They're all 25. I just pick 25. Here I pick 84. So now this feature map, I will do pooling. And when you are doing pooling, sometimes called subsampling, because you are just sampling it down, right? So this big image, we started with a 28x28, will now be changed to something, and depending on the sizes and then how you are going about it, will now become this only size, only 4 things, right? But you see, it's as if it's like you have shrink the image, but the thing is that you have picked the important part of the image. But we also have something called average pooling, where let's say when you pick the 2x2, add all the 4 numbers and divide by 4 and come and put the answer there. So some people use average pooling or max pooling. So depending on what you are doing, you can decide to choose. But almost everywhere now we use max pooling to shrink the image. After we have done pooling, so this pooling, I pick the 9, pick the 7, pick this, pooling. After pooling, we have to send the thing to the, so as we have already said, CNN usually use multiple convolutional layers and pooling, right? Early layers will detect simple features like lines and edges. So we have a convolutional layer, another convolutional layer. Inside one convolutional layer, I'll have a feature map, I'll do ReLU, and I'll pool. Then after that, I go to another convolutional layer. You see, this one I did, I got 2x2 matrix. Sometimes when you finish this, you still have about 10x10 matrix, but you want to reduce the size more. So you want to have another convolutional layer. Get new filters, multiply, the size of the feature map will reduce. Then you do pooling and get the size smaller, so that you now send it to the normal neural network. So when we are sending the final, after pooling, the answer we get, if you are sending it to the normal neural network, we do something we call flattening. You have to arrange these numbers as input to a neural network. And then this is the output. So we'll pick this number, come and put it here. We'll flatten it. It's like we are rearranging it, flatten it. So see flattening. And if it's a 3x3 image, like a colored image, you pick the numbers like the blue numbers, pick these numbers. So I don't talk much about colored images now. Just know this for now. So we'll flatten it, and then this will serve as the inputs to a neural network. Now, the question is, why do we go through all these convolutional steps before we give it to a normal? Why don't we give it straight to a normal neural network? Don't forget our image was 28x28. What is 28x28? It's about 784 or something. Let me check and see. 28 times 28. My time is gone by 10 minutes. I'll finish right now. 784. So what it means that you will need 784 neurons before you can give every pixel to. The thing is that when you go, you can go and try that for a normal neuron, it will work. But can you imagine 784? What if you have a 32 by 32 image? What of a 100 by 100 image? Your neural network will be so big. So we want to go with convolution, because convolution will reduce the size at the end of the day, but still will know the important features and be able to do detection. So after that, we'll give it to a normal fully connected layer. And as we have described already, we'll make it a one-dimensional, we'll flatten, and it become one-dimensional data, give it to a normal neural network. And then we'll put a softmax if it's a lot of output you are predicting. So the one that we wanted to know a car, a cat, and this one, we put a softmax. If we wanted to know a cat or a dog, two things, we put a sigmoid function at the output layer, right? Good. So the output layer, if I'm doing classification, I'll use a softmax function. So if it's a cat or a dog, I'll get to know, right? If it's only two things, you use a sigmoid function. But the thing is, what if you are predicting a number? Because by hardly do we use convolutional neural network to be doing regression work, but still it can be used, right? So if you are predicting a number, even in normal neural network, let's say you are using neural network to predict the prices of things, the output layer, you can use a softmax activation function. You can use a sigmoid activation function, but to give you one or two. So you have to use a linear function. Y equal to mx plus c. You have to use a linear function, right? And you can use a ReLU function too. So you use a linear function, then you can fit and get the output. So if you are doing regression with neural network, the output layer will have a linear function. Good one. So I've explained stride. So let's see a stride of 2. A stride of 2 means after this patch, I'll move 2 and go to the next one. I've explained stride. So we get this. So depending on your filter size and your stride, you will know the size of the feature map that you get. I don't want to go much into it. Now, I want to talk about one last thing called padding. Padding. Most of the time, you want to pad the image. Now, can you see that? Let's say you have a 3 by 3 image like this. If you do convolution, you realize that, you see, let's see this image here. Let's say I'm using 2 by 2 filter. If I do convolution here, when I move, I'll go and do the next convolution here. Have you noticed that this 1 and 4, they have become very important because, you see, during the first filter, that multiplication, it was inside. During the next patch, that multiplication was inside. So at least all the numbers will have opportunity to come in several times. But I realize that the numbers at the edges just have only one chance of coming in. So if you have an image like this, where maybe somebody's nose is around this point, if you don't do padding, you'll not be able to detect the person's nose at the edge there. So most of the time, we put zeros around the image. So if it's a 3 by 3 image, so that it becomes a 4 by 4 image, to be only zeros, so that I'll start the patching from here. The next time I move out, so that the numbers there, I can multiply them several times and know what is actually happening there. I hope you understand padding. You pad with zeros. You pad with zeros. So the formula I wanted to talk to you about is here. Don't worry, those who want to know, depending on the size of your image N and the number of padding P you are using and the size of the kernel you are using, you'll be able to know the size of your and then the S is the stride. You'll be able to know what will be the size of your feature map. Let's see an example. If the image first, this image was a 3 by 3 matrix, so N is 3, it's a 3 by 3, the image is 3 by 3, plus 2 times, how many padding are we using? We are just adding one. Sometimes you can use 2 padding. It means I'll add another 0, 0, 0 around, so that becomes 5 by 5, right? So you can do more padding or less padding, right? So 2 times, here I'm using a padding of 1 minus the filter size. I'm using a 2 by 2 filter, so minus 2 divided by, I'm using a stride of 1, right? So divided by 1, then I'll get 4. So I know that the feature map is going to be a 4 by 4 matrix. But I don't need to know that. The model will just do it, and you just give you the feature map, so you go forward. That's all. So let's just run through all that the things we have done. We are finished. If you have an input image, you do convolution without, you know, the edges and textures and shapes. You do pulling and pull the important parts. If it's a cat you are detecting, you'll be able to get the cat's face within the deeper layers, give it to a fully connected layer, and you'll be able to predict a cat with confidence. So let's see as an image. Let's say I have this, I want to predict. I'll have a convolutional layer. I'll get a filter, a kernel, multiply, get feature map, but I will not have only one feature map because I'll use a lot of filters. So I'll get a bank of feature map. I'll do pooling for each of them and get a bank of another. So when you do pooling, that what you get is still a feature map. So we call it pooled feature map. Then after that, I'll get new filters again, do another convolution. Then I'll do another pooling. Then now I can flatten the numbers and give it to a neural network. Nice, we finished the work. Now notice that actually, if you are training data, you have actually just trained once. Actually, you have to come back and adjust weights and do all the things I spoke about in neural network and adjust the filter because the filter, you randomly use any numbers. So during the first epoch, you'll not be able to do correct because you are training. You'll not be able to do correct detection of the image. But then as you go back and forth and change the filter numbers, those are the weights, right? Keep adjusting them, you'll be able to detect anything you want to detect. So you have a number 3 you want to detect. Let's say you are using a 5x5 matrix and you get a filter, you multiply them, you get a feature map, you pool it, you get a small size, you get new filters, you do again, you pool, you flatten it, you give it out. I hope you understand. The video will be there so you get it. So let's say you have a 2D from a paper, you have a simulation data, you want to, maybe you have a semiconductor wafer, there are some spots on it, or I've not gone to object detection yet. Here we are just trying to say there is a defect or no defect. You want to check, right? You have a lot of data. You give the data as an input. You get a kernel, several kernels, a lot of kernels. You do convolution. You get a lot of feature maps. At the end of the day, you do pooling, get new feature maps. Then go and get new filters again. Go and do convolution, get new feature maps. And then you pool. After that, you flatten and give it to it. Good. So we finished neural networks. What are the convolutional neural network? What are the advantages of CNN? There's no need for a human being to be adjusting the filter for us. CNN filters adapt automatically, and that you can read on that. So there are various types of CNN. A lot of people have developed different steps. Somebody says, go 3 layers before you flatten. Somebody says, even at the flatten layer, the deep convolutional layer, the neural network part, use this number of hidden layers, right? So it started in 1998 by Linus, one of Google's people, and then he brought the normal architecture I've just shown. Then in 2012, this AlexNet came, and you see all of them are following the same steps. Maybe AlexNet came and said, oh, let's use ReLU activation function. There's something called dropouts. Maybe another time you know it from a neural network. Sometimes some of the neurons may not be participating. So you have to take them off this one. It's called dropout and all that. And then he trained the model using GPUs and all. And then he was able to get good accuracy. There's a data set called MNIST data set, which I'm coming to simulate shortly. Then we close, right? It has images of numbers between 0 to 9. Then we wanted to detect whether the number is 0 or 1 or 2 or 3 or 4 using this convolutional neural network that we have just learned. So we have Google Net, we have ResNet, all of them just have, this one says that use 100 plus, use about 100 plus layers, right? And then he was not having any vanishing gradient. So these are all different types. You can go and read about them. We have Google Net, we have VGG, and that one was using a 3x3 filter and all that. MobileNet brought something called depthwise convolution in a special way. And then this brought us to the end of. So in summary, you do convolution, activation function, you pool, get your feature map, you flatten it for a fully connected layer, then get your output. Thank you very much. Any question? And I will take us through short. I've used the time. I've gone by just 19 minutes. 11 minutes, we'll finish the other side. Let's do a scan through. I think I've sent the, let me stop sharing and share my screen quickly. Oh, where is my, unless I share my entire screen. let's go through how we detect some image in a small, oh, this thing will worry me. Let me put it on there. Okay, yeah, to come. Let's go through some small coding here. Maybe I'm sure another time get a lot of time for it. Now, when you are doing deep learning, most of the ones that we have done, when you are doing normal machine learning, we have something we call sklearn, scikit-learn, right? They provide libraries that we use for most of the machine learning that we work. And they make machine learning so simple, sklearn, scikit-learn. So most of the coding pattern that we are using in the libraries are almost all scikit-learn libraries. But when you are doing deep learning, scikit-learn doesn't have a lot of libraries for you to do the deep learning. So there are two libraries mostly that you have to use. We call one TensorFlow, and one is called PyTorch, right? So these are all frameworks, TensorFlow and PyTorch. Now, TensorFlow initially was difficult to code because the steps were so difficult. You have to know and call something tensors like your data. You have to arrange it within a certain side and all that. Was difficult to do the programming. So we have something we call Keras also, right? But now TensorFlow, developed by Google, combined with Keras to form TensorFlow Keras. And they made programming these deep learning models short and simple. But I can also use PyTorch. I'm using TensorFlow here, right? So most of the time you have to import TensorFlow, and then I'm importing something we call matplotlib, and we use that one too. All the machine learning we've gone through, we use this matplotlib so that we can plot graphs and everything. It makes graphs easy. Now we are going to use this MNIST. So I just want us to print that we are loading the MNIST data set. MNIST data set is just it's a handwritten Digit data set, right? And it was gathered about 70,000 of them, where 60,000 has been kept for. So can you imagine this number of data sets, 60,000 images of either 0, 1, 2, 3, or 4, or 5, right? And all these images are there, and we want to see whether we'll be able to develop a deep learning convolutional neural network model to be able to classify whether it is 0 or 1 or 2 or 3. So we are doing classification, right? So we want to import the data. The data is online, and I can't go and pull all the 60,000. So you can just call it, because it's online, you just call it using this. And because, as I said, TensorFlow and Keras have come together, you just do tf.keras and dot data set. It means that you want to import some data set and mention the name of the data set. So depending on any data set you are using, you can change the one here, import the data and say load data to load the data for you. So here I'm just printing so that you know the number of training, because it has already been grouped as training data and testing data already. So here you are printing the training data, printing the testing data so that you can see, right? Now let's see. And then because we are loading the image from online, I want you to see some of the image. So this line is actually plotting some of the image using a figure size of 10 by 4. I want to plot about 10 of the images. So I'm using plot.subplots. This is helping me do subplot. What it means that I can have and the figure. I want 5 of the image to be in a row, another 5. So I have 2 rows and 5 columns. So that's why I'm using 2, 5. And I want to pick all the image one by one. And then it's a grayscale image so that you see the images in black and white, so that we can visualize some of the image. That's what we are having here. And because I've run already, we've sent you the code already. Go through that. When you run, it will load the data. And this one is showing you some of the data, right? Showing it to just display some of the data. So can you imagine, you see, knowing that this is 5 is not easy. Even a child may fail, right? And computers find it difficult. Can you imagine that? Most when you go online, we ask you, are you a robot? Choose the number. Which number can you see? Is it M or N or alphabets? Because when you tell numbers, this convolution, as we are picking and we are downsampling, we are pulling and all, sometimes we may miss the important part of the image and get the answer wrong, right? So sometimes it will not be 100%, but as people have developed with Google Net, Efficient Net, and all the number of layers, somebody say using number of filters and all, we are improving in terms of detecting images. And very soon robots, so most of the robots and all that, we have to just put a CNN model within them, and they'll be able to, when they see something, they process it and know. But now we have something called vision transformers that is taking over this CNN, but this CNN is still powerful and it's able to do that. Now, one thing I wanted to talk about when I was teaching, I didn't talk about is that, the images, when we change them to pixels, it's a number between 0 and 255. We have already explained in our machine learning that most of the time you want to do normalization. You want to scale the number between 0 and 1. So most of the time, though I thought that the pixel numbers, and I just continue, when you get the pixel numbers, you want to change them to numbers between 0 and 1. So most of the time we divide by, use this. My mouse gone off. So here, so we have displayed some of the image, mostly divided by 255. So take the training data, S string, divide by 255 and still call it S string, right? And then take the test data and divide by 255 so that we can get the image in numbers between 0 and 1 before we will do the convolution. We get the filters and do the convolution. And most of the time, you want to check the shape well. You know, one thing is that this MNIST data set, the image is already 20, so just see it's a 28 by 28, and it's a black and white image, so here should be 1. When you change here from 1, you miss it. Your code will not run, right? Most of the time, you put this -1 here, and this -1 is mostly there to make sure that, you know, the data coming is 60,000. And these data, sometimes they are online, they keep updating them. Sometimes the size that the data in Python that you should know. I hope you can hear me saying my you put this negative here so that no matter the size to do that. Now let's come to the main CNN. This is the main part I want you to know. The rest are just plotting graphs. This part, we use this function in TensorFlow, tf.keras.layers.com2d for you. You don't need to do programming. This filter, go and after move. No, you don't need to program. That's one nice thing about this. So you realize that most of the machine learning, if you want to do decision tree, remember the decision tree we're doing, those number of trees, you have to do the programming to make sure you split the tree. Right? So just that if you are doing deep learning, you can't use the scikit-learn because they don't have libraries really for convolutional neural network and all the other transformers and all those things we'll learn later, right? So you have to use TensorFlow or PyTorch. People like PyTorch a lot because they said it's more Pythonic and then it's able to do things so easily for you. But like when Keras came to TensorFlow, make things easier. All I do is tf.keras.layers.com2d. Then you put into brackets, you put a number of filter here. So I'm saying I'm using 32 filters. What should be the size of the filter? I'm using 3 by 3. Now you see, it's your understanding of the convolutional neural network that will let you write this line. And this line is the one going to do the work, right? When you change the filter size, your results may change and all that. So sometimes this filter size and all, they are all hyperparameters. You can do tuning and changing them with time to see what will happen. But the more you are tuning and changing them, you need more computer power. I'm running this thing within Colab because I have access to GPU online so that the thing will run fast, especially with what we are learning now, right? So we know that I'll put the number of filters, the size of the filter, then I'll write activation and write the name of the activation function I want to use. I'm using ReLU. Then I want the model to know that the input data coming, the image is a 28 by 28 image, and it's one channel, it's a black and white. When you see one there, it means there's a black and white. If it was a colored image, I'll write almost the same code, I'll just change here to 3. Right, so let's start, you can go and see the CIFAR data, ImageNet data set, which is a colored image, and you can just modify this whole code and to be able to do for colored images. Then after I have done, so when you call this function, it will do all the multiplication with the filters and all that and give you the feature map. But it will be at the background. Then when the feature map is done, you call tf keras layers.maxPooling2d so that you are saying that, and then you give the size of the pooling. As I say, you have to size the pooling size. But you see, I'm using max pooling. You can change it to average pooling. So you use max pooling and to do the pooling for you. So you have finished the first convolutional layer. Then you go to the next convolutional layer and write the same code. Just that you see, as I said, as you go deeper into the convolutional layer, use more filters because that's the time where you can detect people's faces and map. because now you have a lot of neurons that you have a lot of filter multiplications going on so that I can get sizes, shapes drawn well, right? So here you realize that I'm using, so, okay, I'm here from 2D, just that here I'm using 64 filters in the second convolutional layer, the same activation function, and that's all. I don't need to specify the image again. One nice thing about tf.keras is that, this 28 by 28, it will change to become something like, the normal size, you are using a stride of 1 and everything, and a pooling of 0. So this 28 by 28 actually will change to about 26 by 26 image. But I don't need to know the size that it will become, because this tf.keras will cater for it already. That's not one nice thing about these libraries, right? Good. So you specify 64. You don't need to specify the size of the feature map that will come. It will automatically know the size of the feature map using the formula I showed you. Then you do another pooling. Then here I'm just using 2 convolutional layers. When you go, you can go and add another, just copy the same thing and just change the number of filters. And it actually improves your results, right? Just that the more you do, because something overfitting, you'll be overfitting the thing and all that. And then sometimes it will take a long time to run because you're having a lot of filters doing multiplications, right? After that, you flatten the image. So Keras has a TensorFlow has a nice function called TF Keras layers.flatten, and it will do the flattening for you. You don't need to do anything by yourself. Then after that, you give it to the dense layer, the normal neural network, or we call it the fully connected layer. So TF Keras layer.dense, you say that you are using 64 layers, right? 4 layers. And then, hey, I'm still on the yes, I'm at the dense layer now. So 64, then activation function. So that the dense layer is normal neural network. We have to also provide activation function within the neurons. Then after that, the output layer, and they all use tf.keras.layer.dense, all right, but the output layer, depending on what you put there at the end of the day to get to know the outputs. So because I'm detecting numbers between 0 to 9, means that I have 10 different outputs I want to predict. So that's why I'm saying the output layer should be 10. And then I'll say the activation function is softmax. tf.keras.layers will automatically know when you end here, it will automatically know that this is the output layer and the rest are convolutional layers. This one is the deeper layer. To automatically know that this is the deeper layer. Because this is the last thing, it automatically know that this is your output function. So you don't need to specify that it's really the output. That's all you run, and then you're actually done with the model. You run, and all the training data will run through, and then you get your training data. But for you to run, you have to specify the optimizer. Now, you realize that when I was teaching you neural network, you have to do back propagation. That back propagation that we are doing, we need an algorithm to be doing it. That algorithm that we use is called the optimizer, right? To go and change the weights, because we will not be the ones inside the machine to be changing the weight. So we use different optimizers. So we have stochastic gradient descent, we have Adam optimizers. They actually do the weight tuning, right? So just that most of the time, Adam is very popular, so we mostly use Adam, right? Then you have to specify the loss function. Now I realized that when I was teaching the neural network, I used the mean square error. But mean square error is used for when you are doing regression work. If you are doing classification work, you have to use this categorical cross entropy function. Is the function we use for classification, and we use the mean square error for regression work. But because I'm doing classification, so don't forget this one. So the loss function, always code this when you're doing classification work. If you are doing regression work, you just change it to mean square error. Then when you say metrics accuracy, it means I should show you the accuracy after I run the model, right? Good. Now, as we learned about how to run your code, you have your data. Now your data now is the features. As I said, deep learning will know the features by them. So you don't have to tell it the features. But to get to know the features, you run through all the convolutional layers. You want to train. So you do all the models. I've already done the model here. This model, you take it and say model.fit and say X train, Y train, so that it will do training. It give you the X, it give you the image, you show the number. Give you the image, show the number. Give you the image, show the number. So the model understands and adjusts the weights. And you have to tell the batch size. I've already spoken about batch size. You give it the batch size, say 100, 128, any number, right? So that to go in batches. After every batch, it will update the weights. Then the number of epochs, as I said, you give all the data. So you give the 60,000. So you are trying to say that give the 60,000. After, come back again, give the 60,000 again 5 times. so that the model will understand the data very well. So epochs can change the number to 5 to 10, but you don't need to have a lot of more epochs. If you do plenty epochs, you will let the model overfit. It will learn the data very well so much. It's like I'm teaching you, I teach the thing 100 times. You know the thing so well that if I give you a quiz, you may fail if the questions are different. Now, one nice thing about TensorFlow is that there's this function here called validation split. The number you put here will let you know how much data you should use for validation. So realize that here, you didn't see me using train test split, because train test split is a function in sklearn. I'm not using sklearn here, right? I'm using TensorFlow. So you have to put inside here validation split and say that you are using 10% of the training data and it automatically know to pick 10% and automatically know that let me take 10% and use. This verbose is, when you are doing the epochs, it will be showing you, oh, this is going on, this is going on. Can change it to 0 so that you don't see that things are going on, right? So when you run, so as I said, you see that first epoch, you'll be seeing the accuracy going on, and the next epoch, the accuracy will be improving, So when you run it, will just finish the machine learning model. The rest of the thing is doing plots, right? For plotting, it's something that you have to learn in Python, how to plot, right? So these are things that you can learn by yourself. So these are plotting, you plot, and that is all. You can now make predictions using this. And then we are good to go. And that will be the end of it, right? Here, I'm just counting the number of predictions. You don't need this side. This side, you don't really need what is going on. I'm just printing the number of correct predictions I was able to make at the end of the day, right? So this is the main place you use for prediction. So you say prediction is equal to model.predict. So you have done the training. As I said, this is just plotting. You did the training here, okay, you build the layers here. Then did model.fit. This one does training. Then come and do model.predict. This one will do the testing and the results will be there. Now, when you have the results, you can plot them. You can write it as a table or anything, right? Here, I'm just writing a function to show about 15 of the images I predicted to see whether I predicted the right thing, right? That's here. So you just have to say for I want to show 15 of the images. I do subplots. I'm saying 3 by 5. I mean that I need 5 columns. I need 5 of the image up, the next 5 down, the next 5 down. So you can change the numbers you want here. Then you say that you want to show plot.im show, and then you say that the test set, you give the test set to it. I'm just wanting to make sure that the shape is in 28 by 20. Then you specify the color. It's in grayscale. You specify the color. And then you want to, the prediction that comes, I want to show that I actually predicted, if it's 1, whether I predicted a 1 or not. I use this one to show that what I predicted was there, right? Then I also want to display the main label. So maybe I have a picture. The picture is 8, but I want to see what I predicted. So this part will show what I predicted, and this part will show the real number to see whether I predicted the right thing or not. That's all. These are all trying to plot numbers. And you realize that I did something here. Confusion matrix is mostly in sklearn. So I just did something here to plot the confusion matrix. Realize that now I'm now importing. That's why I decided to just finish everything with TensorFlow and use sklearn or scikit-learn to do the confusion matrix, because they have a certain function called confusion matrix. And then you just say the true values and what you are predicting. And this one line will do the prediction. The rest are plotting, right? So that's why mostly we use sklearn when you want to plot confusion matrix. So when you run that, that's all. So when you run the training, this is the training curve. The red one is showing you the validation, because we splitted and used the data for validation. Then the blue one is showing the training. So realize that the training accuracy keep increasing, right? And whilst first the accuracy was this, when we validated, the accuracy was this, and the accuracy, when you are training, the accuracy keep changing, right? Depending on the number of epochs. So at the first epoch, 1 here, I was getting an efficiency around 97%. As the epochs increase to 2, the efficiency, the accuracy increases. So as the epochs go, so most of the time you want to do this plot so that you actually know this point of intersection here. That's around 3.5. So it means that most of the time you don't want to do 3.5 epochs. So it means that at least even if you do 3 epochs, it's fine. The model will be able to understand the thing very well. You don't need to do a lot of epochs. So that's why most of the time you plot this one. And also plot your loss function. The loss function means you want to see the differences in your predictions. The lower the value means that you are actually making good predictions. So you sometimes plot the loss functions too as well. So this is the display. I'm just displaying that this number was 7. So that code I just explained, say the true value is 7. So show the 7, but then also show the prediction I made, right? The prediction I made 2 is 7. So realize that almost all the ones I displayed, it was 2, I predicted 2, 1, I predicted 1, and all that. And that is also at the end of the day to give me the accuracy, 98.99%. Now it's not straight, it's not like I've done anything big. This data has been there a long time, and people have found different ways. You can go and use the ImageNet, the efficient net, and already trained models. People have already done the coding already. They can pick it and give you that data to give you higher accuracies, right? And this one is giving the confusion. We have explained a lot of time what confusion matrix is. Here, just tell him the number of 0, and here is 0. It means that the numbers that were 0, I predicted 978 of them correct, but I missed only 1, and I missed 1 and 1. That's 2. It means that the thing was 0, but the model predicted it to be 7. And then it also missed this one time. The thing was 0, but I was trying to say it's 8. Let's see one that is plenty. Let's see this number. I hope you know how to read your confusion matrix now. The number was 5, but then I predicted 4 wrongly. I was able to get 880 of the 5 in the data set correct, but I predicted 4 of them wrongly. Let me see what I predicted. It was 5, but I thought it was 3. That's what the confusion matrix is telling you. So all the numbers here are telling you the numbers you predicted so well, and the numbers here are telling you the ones you missed. And you can come down to see which number it was thinking it was, right? We have spoken about precision recall F1 score already. So I want to leave you here, and that brings us to the end of convolutional neural network. I hope you enjoyed it. I hope you understood what I said. If you didn't, the video will be available for you. I've spoken plenty. Any question, then we close. I took another 30 minutes.
Yeah, so I think we have come to the end of another class. And so let's all make it a point to go back to the video if we missed anything. It's been a long lecture, but it's worth it so that we can have this documented and we can all go back to it. So thank you very much, everyone, for coming around. If you have a question, please send it in the chats. Ibrahim, are you trying to ask a question? All right, so thank you very much, everyone. Let's see you next 2 weeks as we come your way with another lecture.
That's a good course. I'm telling you.
Attendance form.
Thank you, sir. Thank you, doctor.
Thank you. I hope you understood.
Very good, very good.
Great. So you can watch the videos more and more, and then you'll be fine.
Those who are waiting for the attendance list, just wait 1 minute. I'll post it.
Good night. Come again, Ibrahim.
I say thank you very much.
Great.
Yeah, very good. Good night.
Good. There are 2 things. Either you understand